We will continue our discussion on Nil-Laflamme theorem. So another application. This is what is called T-error correcting codes. So I will define something for a classical one. This is a classical concept. T-error correcting code. This is just a classical code which is converted to the quantum, which is the analogous one for the quantum situation. So if you have any set S is any finite set. See, of course, any message you will send it from some set. Yes, right. So it will be a S is some set. So the alphabet will come from this, and a word will be in S. Yeah, the cross product S power N. So if you have a word, so if you have any subset containing the Sn, okay. So this is how you will code. Coding is done through some C. Let's see in Sn or some yeah. And S will have a cardinality and all that. So in the background, S will have cardinality. We can define a metric on this D of if we have X maybe tilde, X tilde, Y tilde, and C. Okay. Then you can define D X tilde, Y tilde equal to the number of I such that Xi not equal to Y, where X equal to X tilde equal to X minus X, Y tilde equal to Y tilde. Okay, this is a generalization of discrete metric. If n equal to 1, this is just discrete metric. This is what is called Hamming metric, I think. Hamming distance. So to prove, I leave it as an exercise to prove this is this metric, but it's not direct, it's not immediate. It's not like discrete metric, it's not immediate. You have to consider cases. If you want to really see a video, then I have my analysis course in the first class or something. I have done this. This is a metric. I mean, where we define examples of metric space, where it is done. So this is the distance between any two words in Sn. You can define a metric. You can of course take S1 cross S2 for a general metric. For here you take S. So now if G is a group, instead of S, we take a group. G is a group. Then we can define something like a need not be a metric, it can be a norm. Okay. Then we can define for any X tilde any. No, this is not what I want. Anyway, this can be defined for any Sn, doesn't matter for C or any Sn. This has nothing to do with C. C will come. If G is a group, okay, then for any X in Gn, X tilde in Gn, you can define W of X tilde, the small w, which is called weight of X tilde, is equal to number of, again, X tilde is X1, Xn. Weight of this is weight is number of I such that Xi is not inclusive. I mean, this is like a norm, okay? Because this will determine this. Huh?
Scientific terms.
Zero means identity. G is additive. Sorry, it's an abelian. G is an, we always take an abelian group with additive kind of thing. Additive. Abelian. And zero is the identity element. So this is what we have been using for all our weight representation, additive abelian. Okay, now you define E of C for C contained in Gn. Gn, E of C equal to minimum of, I mean, this is a finite group, okay, abelian, finite abelian. Is it finite set? So it should be it's finite abelian. So there is no, I mean, there's no need to take infimum, it's all finite. Okay, minimum of W of theta is in C. And X tilde not. Here I forgot to say then X tilde, I mean, and X tilde is going to be not equal to the identity. Gn is also a group, but it's not the identity. It's not the additive zero in that. So it is that way. Okay, this is the D of C. So this C, if D of C is something, a number, I mean, it's something big. If it is big, then if we have D equal to 2D plus 1, or I mean, if D is odd, otherwise you have to take it as D is equal to D minus 1 by 2, like the integer part of it. Okay. If you take it, then this C is called T error correcting code. In the quantum setup, it will be clear, because otherwise I have to define it on the classical case. I mean, the quantum thing, we mean something as an error correcting code. If you have a subspace, if your state has a support there, then you have error operators. Then that for states here, for the error operator, you can get a recovery map. Okay, so I am not defining all these things for classical case, but it will be clear. The same thing we will do for quantum setup, and it will be clear why it is called T error correcting code. This is called T error correcting code. So if T is equal to this, okay, D equal to 2T plus 1. Why it comes 2T plus 1, it will be clear. Okay. I mean, in the quantum setup, it will be more clear. Okay. So now let us say, so quantum thing, I mean, in classical communication, other things, sets are finite, another thing, but here it will be finite dimensional Hilbert space. Okay. So let K be any finite dimensional Hilbert space. And you have H is equal to K times Rn. This is the analog of Gn. Gn. Then you define an ET for T, some T less than or equal to less than n, much less than n. I mean, T should be a small number. T is the kind of number within which, I mean, so that the error operators comes from this. So it should be small. It cannot be equal to n. Then everything will be the error thing. Okay, you cannot construct anything. So if ET should be span of all these operators. Tensor Xn, such that the number of I, such that Xi not equal to identity, the identity and the corresponding K, not equal to identity, yeah, is less than or equal to T. So it is all those span of all those operators, elementary tensor, which has identity except, I mean, except the T places. At most T places it can occur. It can be non-trivial. Everywhere else it should be identity. Okay? It is span of those things. Okay? Of course, we have to take the span. It's a vector space. This is what is called T error correcting space, error space. So your error space is this. Okay? Now anything which corrects this is what is called a T error correcting code. Oh no. I press the off button. Now it's okay. Okay. So definition. Any subspace C and by mu, whatever the H, which is Kn, H is equal to Kn. Okay. Which corrects ET is called T error correcting. This is what is called T error correcting. So now we want to construct T error correcting. That's it. So for that we want to use the same kind of error operators. So we want to use groups. Okay. So let G will again finite is additive finite. additive loop. That means the zero is going to be. Then K is L2G. L2G. K is L2G. So we want to get a nice basis for this. We want to have a nice operators, a nice basis for this. How to get this for this ET, for this space, we want to get a nice basis. Okay. So that we can get a holding space. We can get a C, error correcting code. Okay. K is L2G. No, tensor N is H. K is for one single thing. You tensor it N times to get H. Our H will be big. It will be tensor. It's amplification. It's a big thing. In fact, I will be taking L2G power Mn. That's what I will take finally. Okay. So this is this RHA. It doesn't matter. I can just take L2G. There's no big RHA. Okay. L2G. Okay. K is L2G. Okay. Then we have this Weil operators. We have already defined L2G are functions. UA at F at T is f of T plus A. So this is for A in G and alpha in G hat. This is the character group. This is all homomorphism from G to surface. Okay, that is a character group. A of the first is this, and V alpha F is equal to alpha T. Then we have already shown that UA V alpha is equal to alpha of A, that is V alpha UA. Okay, and we call this as W of A. VA to alpha, UA V alpha is WA comma alpha. So it satisfies this relation. There is one more thing. If A alpha is not equal to 0, 1. 1 is the identity character, I mean constant function of 1. And this is the A is additive 0 of the group, A not equal to 1. Then the trace of W A alpha becomes 0. You can check it. That's because UA is just permutation matrix. When A is not equal to 0, this is a permutation matrix. There will be nothing in the diagram. And V alpha, when alpha is not equal to 0, 1, it is going to be alpha. So it will be, this will only be in WA alpha, only you have to sum the diagonal element. That will be summation V alpha X. In place of this will be summation alpha of T in G equal to 0 if alpha is not equal to 8. One of them should happen. If alpha is identity, yeah. Huh? If it is identity, it is just WA. I mean VA alpha. It is just WA. I mean it is just VA. Trace of VA is 0 because it's a permutation matrix where it doesn't have anything on diagonal. It truly shows. I mean, it does the identity, the diagonals are 0. Okay. So because of that, it is. So if it is otherwise, if we have an alpha something, if A is, I mean, if A is not equal to 0, okay, and alpha equal to 1, then it is, then trace is 0. Okay. If alpha is when alpha is equal to 1 and A is not equal to 0, it's 0. Trace is 0. Okay. When alpha is, then the only case left is alpha is not equal to 1. When alpha is not equal to 1, this is what you will get, and that is equal to 0. Then because alpha is not equal. This is Schur orthogonality. Okay. So because of that, trace is 0. So 1 by n power half, where n is cardinality, n is equal to cardinality of G. The dimension of whatever K. Dimension of it, which okay. K. 1 by n power of W of A, that A is in G, alpha is in G hat. This is an orthonormal basis for P of n with respect to rates, not problems. Race. With respect to this Hilbert-Smith inner product, trace inner product or whatever, this is an orthonormal basis. Okay, that's because if you take in WA alpha, WA alpha, when A, if you want to talk about this WA alpha, W B beta, that will be going to be another W operator up to your constant. And if A is not equal to B, alpha is not equal to beta, then that is not going to be identity. So that trace will be zero. Because of that, this is not the trace. So that's clear, right? Now we consider H equal to some L2 G tensor N tensor of this. Okay. So notice that in general, sir, L2 of any X, like X is a nice space. Finite space, there's no problem. It can be easily identified. Even if it is topological space compact or something, then also it is tensor N. The same as L2 of X. There is an identification. The identification is here it will be F1. And you have to see, identification means there's a unitary between here to here, which is it's a unitary. Okay. Inner product preserving bijection, that's what we want. So if we take F1 up to Fn, and it's enough to define bijection on a total set, even in infinite dimension, it's enough total set, and that should give you a total set there. Okay, let's know even for infinite dimension. But here in finite dimension, it's enough to take orthonormal basis to orthonormal basis. That's fine. So if F1 tensor F1 will go to some function, some F, where F at any, here it will be X1 of X1, what it is. It's just F of X1, F1, X1, F1 is the problem. So with respect to this, you can verify that this is a unitary, and that is an identification of this with L2 of Gn. Both you can identify. Okay. Now for A tilde in Cn and alpha, again, Gn's character will be G hat N. That also you can see. Okay. So alpha tilde in G hat N. Yeah, N times. Okay. You can define W of A tilde alpha tilde equal to W of A1 alpha 1. So W of A alpha A, W of AN. We just take the intuition. Okay. And here there are N of them. Okay. So if you take, the trace is only when everything is, when the trace of this will be the product of the trace, right? And if you want to take the trace of something is non-zero, only when it is identity, and that the trace will be N. N is the cardinality of G. Okay, N is the cardinality of G. So this whole thing trace will be 1 by n power n. So 1 by n power n by where n is this n is the cardinality of G times W of alpha bar, A bar, A bar, A tilde. I use tilde because there will be a bar. I realize that it will be confusing with when I take the bar for that, it will be confusing. So that's why A tilde, alpha tilde. This Gn alpha tilde E hat n is an orthonormal for B of this, or B of that. Okay. So now for ET, we have ET. ET is something which has X1 tensor Xn, where this is not in this tensor span of this, where Xi's are non-trivial at most in T places. Okay. So similarly, if in this W's, if that is at most T places, if it is non-trivial, that will generate that. That's clear, right? Because if this generate, that will be generated. So 1 by n power n by 2 W of A alpha tilde with the weight of A tilde alpha tilde less than or equal to P. The weight is the whatever we have defined for the general, which is the weight. No. It's not that. Not the weight. The weight is not the one. Sorry. The number of places is the other way. Weight is the weight is the, it is not equal to the other way. I mean, weight is for the coding space, not for this. Where A tilde, the number of I, such number of this I, such that AI alpha not equal to 0, 1. Yes. This is the number of I where it is not equal to 1 is less than 1. Okay. I mean, we have xi such that this is the space is number of I such that xi not equal to identity. Okay. This is less than or equal to. That is our ET. That will be spanned by, I mean, in the ith place, you should have the while operator, which all those things, AI, which is not equal to identity. Both of them should be, equal, AI should be equal to 0, alpha I should be equal to 1. I mean, this UA is commutes, alpha is also commutes. I mean, U of A commutes, U of A commutes, V of alpha commutes, but together they don't commute and they generate the whole thing. Okay. Now, when both of them not equal to identity, okay, I mean, then they will generate the whole thing in that corresponding component. Okay. So this is the basis for our ET. Okay. We will use this. Okay. Okay. Now it's clear. Remark. C contained in L2 of C, yeah, reference are n. Or you can put the n inside if you want. Okay. With n from 0 to k minus 1 orthonormal basis is T error correcting, that is, it corrects this error operator, T error correcting, if and only if whatever EI W A alpha A tilde alpha tilde EA equal to some constant which depends on this constant with lambda, which depends on A tilde alpha tilde times delta I. And this constant does not depend on I. When I equal to j, only the constant comes, and that does not depend on I and j. It depends only on A. This is Néel-Laflamme theorem. Néel-Laflamme theorem says the following: if you have a error space, okay, which has a basis Li or something, Ki or whatever, okay, and if you take two operators from the error space, I, L1 and L2, then L1 star L2, if you put it here, this should be a constant depending on that times this. But if here the error operator, so for all A tilde alpha tilde not equal to 0, 1, okay, for sorry, AI not equal to alpha I, for at most for I mean A not equal to I with number of whatever that number of I for all A tilde alpha tilde such that the number of I such that AI alpha I is not equal to 0, 1 is less than or equal to 2. Because you are going to take here one WA alpha tilde that bar, I mean, WA alpha delta star. See, the Nil-Laflamme theorem says that this should be delta Ij for, and it should depend on the operator only, constant. And you will get a L1 star L2, where L1 is an operator like this, L2 is an operator like this. But if you take L1 star, this will become minus, this will become alpha inverse. Okay. And when you take the product, this will be a constant times again this thing. And the constant which will depend on these numbers only. Okay. But you will get an operator again for this. So it's enough to prove for these operators. But if it at most, I mean, if it is in T places, if it is non-trivial, and another one is T places in some other T place, some other T places, it's non-trivial in some other T places. Totally there will be, it can be non-trivial in 2 T places. So that is why 2T here. Okay, that's why 2T here. Okay. So this is what we have to prove. To prove that this is a coding space, C contained in L2G is error correcting for this ET, if and only if for any orthonormal basis for the C, EI, the inner product of EI with this Weyl operator W8, A tilde alpha tilde, where A tilde alpha tilde is non-trivial in at most 2T places. Okay, the tuple, the AI alpha A, this is non-trivial. Together they are non-trivial. One of them can be trivial, the other one can be non-trivial. That's also considered as non-trivial. Okay. So this is non-trivial at most in 2T places. Okay. Then for that it should be a scalar like that. It is just the formulation is like this. The proposition is easy. So this is what I'm going to define is a code invented by Shah, and it is what is called SHAR code. But this is not SHAR code. SHAR code is something simpler. This is a generalization of SHAR code. So generalized SHAR code. Example, this is what is called generalized SHAR code. So let's again keep the same thing, L2G and all that. Okay. Let C contained in L2G. Yeah. A subgroup. Sorry. We wanted a classical. Sorry. C contained in Gn. Okay, a subgroup. Gn is a group. Those direct power subgroup. Okay. Which is here means this whatever this W still path in C. This minimum is equal to D, where D is equal to 2. That's how we define it. That's how we define it. Okay, the class. Okay, that's what it is. Okay, so the C is like that. Okay, then you take C hat. C is a subgroup, so you can take C hat. You take M power of that. Okay. Maybe you can put a C here. I put C because N and M are the back. Okay. Maybe at C. C. Okay. Now you take C and hat of M. Here you define maybe N and M. Contained in this. This is a character subgroup. Okay, it's a character group of C and M. Okay. It's a subgroup. Which is gain. But here the Cn is the code. Cn hat M. This has M of them. So among them, the T is something which is gain T another character. In the sense, if you take a tuple in this, Cn already is a tuple, but this is again an M tuple on that. So there is a NM tuple. But we don't care about the M tuple. We consider that as 183. And among that M tuple, the number of the, which satisfies this condition. Okay? the x delta is not equal to is the minimum thing is t. Here you are taking minimum, for the error thing you are taking the maximum. You can see that why we are taking. Okay, this will not intersect. That's why. If the error space is small, then we can get this coding space, which is big. So which is T error correctly. So we have this information, Cn and Dn, okay, which we have. Now we want to define our coding space in L2G. These are all classical one. Okay. We are taking classical one. We want to define the quantum thing. Okay. Now we will define for alpha in Cn hat you can take, or Gn hat you can take. Cn. You define, maybe I use let's do it. Like chi equal to chi1 chi1. Okay, in Cn hat m. This is okay. So then you define f of chi x. It is just chi x only, but you have to divide it by 1 by the number of elements in Cn or half to make it 1, because you want an orthogonal system. Okay. Maybe I put an x tilde here of f chi x tilde, where x tilde is in L2 of G. Yeah. X tilde is in Cn. And equal to 0 otherwise. And for I mean this is an element. This f tilde f chi I is an element of L2 of G n. L2 of Gn or whatever, which is L2 of G. Yeah, else are there. You take chi equal to chi1 up to this. You take a chi I. Okay. Chi I is in the Cn hat. Chi I is in Cn hat. Each chi I is in Cn hat. Okay. So you take a chi I equal to 1 to m. Chi I is in Cn hat. Okay. And f chi I acting on any x tilde is just f. Sorry. Chi I. I mean, I am writing the same thing. It is just chi I of x tilde. You can just write chi I of x tilde, but you want to divide it by this number. So that's why using this. Okay. Okay. Now you can see that. So then you can define f chi of this equal to f chi1 and f chi2 is f chi yeah. This is in L2 of G n tensor m, which is same as L2 of G n m. You want? These are all acting on L2 of Gn. So this is L2 of Gn tensor m times. It's the same as L2 Gn, whatever. Okay. Now let's see equal to span of. You can verify that f chi prime equal to, it's an orthogonal basis I want to verify, which is equal to, this is just the summation over this. Okay. If you take this, this is just going to be the energy of Cn, right? The summation of chi, I mean, it's a product of all those things, right? Cn power m, yeah. I mean, so Cn power half, Cn power m by 2 you will get. Okay. And that is what the cardinality of that. I mean, I mean, this is not, I mean, all I want to say is, if chi equal to, this is equal to the product of I equal to 1 to m. Okay. The 1 by, this is just, you can take it out. Cn, cardinality of Cn power m by 2, okay, into the inner product of this. I mean, this is the summation, the inner product of x bar. And forget about that. Chi is, no, you don't need to. Which is just 1 by the number of elements in Cn power m by 2 into summation of chi of x tilde bar chi of x tilde. This is time where x tilde is in Cn. Cn hat power. You have a constant which is the number of elements in Cn power m by 2. Summation where x tilde is in Cn hat power m. Can you see? Cn hat power m. X tilde is in Cn hat m. Okay. Then chi of x tilde bar chi of. Okay. This is equal to delta chi tilde times the constant. But when chi equal to chi delta, that is the constant. That's the cardinality of that is, it will be summed over this. This cardinality of this is exactly this. Okay. So this is equal to. When chi not equal to chi delta, this is chi bar chi of x delta, which is non-trivial when they are not equal. So when you sum it over, it will be 0. Again, sure orthogonal. Okay, is that okay? It will be 0. So when they are equal, it will be 1 summing over 1 everywhere. And that will be number of times it summed is the cardinality of this. Cardinality of this thing which is equal to this. Sorry, there is no by 2. There's Cn by 2, 1 here, you get here, so Cn power m. That's what we. Yeah, the by 2 will go. So this is okay. So it's an orthonormal basis. Okay, let me recall what we have. We have a G, we have taken Gn, we have taken a Cn, which is a T error correcting code, whatever it means. Okay, that is because if you take the W of x of this, that will be minimum of, minimum of that weight is going to be T, where D is 2T plus 2. That is for Cn. Similar thing, you have a Dn, you take Cn hat and you take it to the power m, Dn, you have this. Okay, this is what you have, T error correcting. Okay, now you using for anything, so this is for, I forgot to say, this is all this chi is to come from, so I'm sorry, I'm extremely sorry. This has to be Dn. Where are we using? So what's this time? Sorry, so this is not Dn, this is Dn. Right, then only it makes sense. Dnm is, it's not for every Cn. No, every Cn head you can define. But we are taking, okay, every Cn head you can define, that doesn't matter. But we are taking, I mean, I have, that's okay, I haven't said anything wrong. But every Cn head you can define. But for any something in Dnm, we have this, and then we take the span of that. Okay, that is what will be our coding space. Okay. So we have a Gn, inside Gn we have Cn, and Dnm is in Cn hat m. Okay. For anything, any chi here, we define something like this using that. We have that's an orthonormal, that's a mutually orthonormal vectors in the L2 of corresponding L2. Okay. Then we define C to be span of this. Right? That can easily be. Okay, now this is the proposition. Okay. C is P in this place, the 2 of G N tensor. L2 G taken N NM times. You know, it's okay, you can take a very big space. And if T is small, then you can get the other T for this. But this is what you want. So proof. By nil left line, we have already said what we have to do. We have to take WA alpha, where this is less than or equal to 2T. We have to prove that this doesn't depend on that. It's a direct verification. We have to. Okay. Need to verify. Verify. To take an F for any two orthogonal basis, we have to verify that F and we take a W of A delta alpha delta. Okay, we will take it and we will take an F prime. Okay. We want to prove that this is equal to delta of chi A prime times constant which depends on A delta alpha delta. This is for all A delta alpha delta with the weight of A delta alpha delta. Not weight, sorry, again I am saying the same thing. With A delta alpha delta for all alpha deltas with number of I such that it's not going easily. Number of I such that AI alpha I not equal to 0, 1 is less than or equal to 2. Is for all A alpha such that it satisfies this condition 2T. We have to verify this. Okay. Where this is some constant. Okay. So when chi is not equal to chi prime, we have to show it same. So we take a WA alpha, which is of course UA V alpha. So we consider this. Right. Right. Both in D and FJ, UA, V alpha, F. You want to consider this. Okay. Okay. F chi is going to be the small f, this, right? This. F chi is going to be this. F chi is going to be this tensor product of these things, where each one is given by that character. Okay? That's what F chi is. So this is equal to whatever that 1 by talking about that Cn. Okay. Like that it will be Cn power m, whatever that is there already. We need not worry about it. This is just a constant. We need not worry about it. Okay. That is just to make it orthogonal. So I just write the constant, some constant, lambda. Then this is going to be pi. Pi is a means product, of course. I equal to 1 to m. Okay. F of pi. If you bring u, this is A is A delta alpha delta. A delta alpha delta. And another thing is this is going to be summation, right? Some constant times summation of it's delta in Cn. Yeah. Right? This is L2 inner product, so we are taking the sum. Okay. and it is going to be F. Chi is going to be, I mean, this chi is going to be chi1 up to chi m, so chi I of this x as a x1 up to xn. This x s is a tuple. So that tuple, and let me not write everything. This x is the tuple, x delta is the tuple x1 up to xm, and chi is the tuple chi1 up to chi m. Chi prime similarly chi1 prime up to chi m prime. This xi, this ua delta will go here as u minus a. Okay, and u minus a will shift it by minus a, and each one it will shift. That is the tensor. Okay, it is going to u xi minus ai. That's what you get. Okay. And so I've written the constant there. So this is going to be chi a of this. By definition, this is just chi a of this. Chi a of this times. So now V alpha acting on that. So that is just chi I prime of the same xi times alpha of alpha I alpha I, this is chi I prime of xi. So the alpha I of xi. Correct? Huh? Bar. Yeah, there's a bar. Now it's correct. No, UA will act on that, and that's what you will get. And sorry, you have a product of this. You have a product of this. Okay, there's a product. Okay. Okay, you have a product of some, and then there's a product. Then you have all these things. Okay, this is the expression you have, and multiplied by some constant. We don't care. Okay. Okay. Now, this xi minus ai is in Cn plus a. I mean, nothing minus a plus a, right? Okay. Now, weight of Cn is d, and this ai is not equal to 0. I mean, this. This a. This a is also in Cn. I mean, where is this a coming from? A is in A coming from Cn, right? Cn, which is contained in Gn, right? A itself has n coordinates. We are using only m, but this is the whole thing is happening in nm tensor. So this Cn is in Gn. So each A has n coordinates. Okay. So the number of things which are not 0 in this AI, this has a coordinate. A has a coordinate. Number of coordinate which is not 0 is less than or equal to 2t. Cn, where the number of things less than or equal to, where not equal to 0, is greater than or equal to 2t plus 1. So Cn plus A is not in Ca. Okay. Since W of x theta, whatever W of g theta is greater than or equal to 2t plus 1 for all C theta in Cn. Okay. And AI in in AI, if AI equal to some AI, up to AI, say whatever. Or let me say AI is actually T. AI is T correctly. That's what it means. Not AI is not T correct. Cn is T correct. I am using sorry. I mean, it is just the number of non-trivial A is a tuple. The number of entries which are not equal to 0 is less than or equal to 2t. So here it is 2t plus 1. So AI is not in Cn. So this implies Cn plus AI is not in Cn. So Cn plus AI intersection Cn is empty. Yeah, there is no intersection in there. Okay, that's because this is a group. If it is there, then A will be in Cn, which is not possible. If there is an intersection, A will be there, which is not possible. So because of that, this thing and this thing, they never intersect. Wherever this is non-zero if and only if it is in Cn. This is non-zero if and only if it is in Cn. So this sum is 0. This sum is 0 equal to 0 if A is not equal to 0. is not equal to that 0. I mean, this 0 is in Cn. It's a 0 in Cn. It's a tuple 0. Cn is contained in Gn. It's a tuple 0. Okay. If A is not equal to 0, the sum is 0. Because this will be in Cn plus A. This will be in Cn. They don't intersect. Okay. So wherever this is non-zero, this will be 0. Wherever this is 0, that's 0. So because of that, the sum is 0. So A equal to 0. So we assume, so when A equal to 0, okay, then the sum is whatever that sum we have is equal to, let's forget about the lambda, which is just summation over x tilde in Cn. Okay. Now we forget about the product. The product is same as just chi. I mean, the product of all this is going to be chi of that, the character. Okay. I mean, that is what the character is defined. The chi is the character which is chi1 up to chi m. So chi of any element, chi of a tuple is going to be the product of chi a of the individual thing. That's the product. That is how it is defined. Okay. So this is just chi bar of x tilde, chi of x tilde. Then you have alpha of x tilde. Okay. So which is just chi bar. Sorry, this is prime. Here prime. Okay, prime. Okay. This is now chi and chi bar. They are in Cn power m. I mean Cn hat power m. Okay. Again, the same. Again, if you see here, again, we have taken Dn now. Our chi comes from this. Okay. And not our, I mean, our chi comes from this. Okay. And this is T error correcting means this number of is the weight of anything, weight of any chi. Chi is in this Dn is greater than or equal to 2t plus 1. This is the d. Okay, 2t plus 1. That is what T error correcting definition. Okay, so weight of anything here is 2t plus 1. Okay. And for alpha tilde, the number of the tuple, the number of things which are not identity, not equal to identity, is going to be less than 2t. Okay. We have this chi here. Okay, W of chi is less than both chi and chi prime. W of chi. W of chi prime. They are in deep D and M is greater than or equal to 2t. Okay. On the other hand, the which is the W is defined by that. Okay. The number of I such that alpha whatever. I mean the corresponding that is also weight function. And the weight of alpha, that's also weight of alpha. Weight of alpha is less than or equal to 2. I don't know why I was writing it again. There was some confusion. There was no confusion. This is the weight of that weight of function. Weight of alpha is less than or equal to 2. So again, this is a group, right? This is a DNM subgroup. Okay. So this implies that chi bar chi alpha is not in DNM. Okay. So that sum, this implies the sum of x theta in C n hat power n. That's how the sum is. Okay. Chi bar chi alpha of x theta. That is what that sum is, whatever the sum we have equal to 0. If alpha is not equal to 1. Right, the one in C n hat it's a one there. It's a one of that. One is the identity of that. Identity of that. So if that is not the case, this is going to be 0. Okay. So we have shown that when, I mean, if alpha is not equal to 1, A is not equal to 0, this is 0. Okay. So if alpha equal to 1 and A equal to 0, then that sum is going to be, there is nothing there. So which is the sum is going to be x tilde in whatever C n hat or chi of No, wait. No, this is not, does not just depend on that. Wait. This is alpha is not equal to 1, but at the same time, I mean, chi is not equal to chi prime. I mean, where is alpha is not clear. Alpha may kill the whole thing. See, the point is, sorry. Wait. I haven't said it clear. So, I mean, these DNM doesn't make sense. But I mean, it will not be in DNM, that is clear. I mean, it is DNM is what I said is correct, but that's not what we are using. Okay. When this is what we use, when chi is not equal to 5, okay, and alpha is not equal to 1. Okay. I mean, we have there's the sum is going to be this, like summation of external charge. Okay, chi prime, chi bar, chi alpha of external. Okay, that is what our sum is. Okay, if alpha equal to 1, let's finish this. If alpha equal to 2, if alpha equal to 1, okay, this is going to be 0 if chi is not equal to chi prime, and equal to 1 if chi equal to chi prime. Okay, does not depend on chi. Okay, so now if chi is not equal to chi prime and alpha is not equal to 1, okay, then chi or chi prime alpha. Okay, this is non-trivial. On Cn over here. If it is trivial, if it is equal to 1, then alpha will be equal to chi prime. That means alpha is there. If trivial, sorry, I erased something. That is the argument. I mean, alpha is not in DNM, which we already have. Okay, alpha is not in DNM. I just used it. Alpha is not in DNM. So if I mean, big alpha is not in this, not in DNM. Okay? That's because of the T error correcting thing. It's not in DNM. So if chi prime, they are not equal. Okay, this cannot be trivial. If it is equal to identity, then alpha will be equal to this, which is not possible because alpha is not in DN, which is not possible. So it is non-trivial, so the sum is 0. Okay, so the sum is 0. Okay. So if chi is equal to chi prime, then the sum is some lambda, which is that cardinality of Cn times m by 2, whatever. Then sum of alpha of x tilde. Okay, where we over x tilde. But this is some number which does not depend on chi and k. That's what we want. Okay. Correct? I mean, it should not depend on chi and k. That is the nil left length. Sorry, where you lost? We were computing that inner product. That inner product is on orthogonal basis, chi and chi prime. We have those operators. That should be equal to 0 and chi not equal to chi prime. That's what we have shown in all this. I have erased something, but that part, I mean, it should be in the video. But that shows that alpha is not in DNM. So when chi is not equal to chi prime and alpha equal to 1, this is equal to 0. Okay. When chi is not equal to chi prime and alpha is not equal to 1, again it is 0. That's because this cannot be trivial. If it is trivial, then alpha, if it is 1, alpha should be equal to this. So that should be 0 because of the orthogonality, that is 0. Okay. Now when chi equal to chi prime, there is no chi and chi prime. It will be alpha x tilde, which does not depend on something. That's what we want. It should be 0 when chi not equal to chi prime. That we have proved. When chi equal to chi prime, it is equal to summation over alpha x tilde, which depends only on alpha. So that's all. That's what we want. Oh, I will just give an example because I would say it will be a good idea to do this. Maybe I will do a diagram and other things next time. Where is that? I mean, this is generalized shard code. The shard code is this. Here you take G to be Z2. Okay. And N equal to 3, M also equal to 3. Okay. And you have to define C containing the Z2, 3. Okay. Z2 cross Z2 cross Z2. That is 3. So which is the C is just this. 0, 0, 0. 1, 1, 1. Which is of course a subgroup. Again, isomorphic to Z2, but it isn't this one. Okay. Now we want to define Dn. Maybe call it C3 or something. Okay. So D contained in C hat. What is C hat? C hat is, this is two elements. C hat will also have two elements. It will be identity. The another will be C hat has two elements, which is chi naught and chi 1. Okay. And chi naught is equal to identity. I mean, the constant function 1. Constant function 1. And chi 1 of 0, 0, 0 will be equal to 1. And chi, 1 of 1, 1, 1 will be minus 1. That's all. This is the function. Okay, this is C hat. Now you have to define a D contained in C hat of 3. I mean, C hat as a function, let's write. What is C hat? C hat, this is the function. We want to consider F chi 1, right? F chi 1. F chi naught. Okay. F chi naught is an element of L2 of Z2, 3. Z2 tells 3 tells, right? Okay. Z2, 3. It's this. Okay. What is Z2? Z2 is just C2. I mean, sorry, L2 of Z2. Z2 is two elements, which is same as C2. C2 has two bases. One is 0 basis, another is 1. I mean, C2 has two bases. This and 1. This will correspond to the function 1 at the 0th element. Z2 is 0 and 1. The identity, I mean, the indicator function is 0. This is indicator function at 1. So that is what is this. Okay. Now this chi naught takes this function, the chi naught takes identity to identity. So it will take 0 to 0 to 1 to 1. Okay. And that's what will happen in all those things. Okay. So F chi naught will be, let me just write it, 1 by square root of how many? Two elements times 0, 0, 0 plus 1, 1. It takes identity to identity. So it will take the first year, I mean, the F chi naught will be, I mean, it's clear, no? This is the indicator function at 0, indicator function at 0, indicator function at 0. So that's why that is this. Okay. Identity map, I mean, in L2, there are two bases. Indicator function of 0, indicator function of 1. If you take the sum of that, that will be the identity. So that is what is this. Okay. So the another function is indicator function of 0 minus the indicator function of 1. Okay, because 1 will be taken to minus 1. That is what the thing is. So that is why F chi 1 will be 1 by square root 2 of 0, 0, 0 minus 1, 1. Okay. This is F chi 1, F chi 2. Okay. Now our D is F. I mean, D is a subset, right? D is a subset of C hat two elements power 3, right? Which is going to be Z2 hat power 9. Okay. So our coding space is going to be, so what is D? D is going to be F chi 1. F chi 1, F chi naught. I take the same thing. Okay? Two elements. I am just writing two elements for that. Okay. F chi 1, F chi 1. Another two, F chi 1. This is our thing. So the two elements, that's all. So if you see, the C will be span of two elements, which is just 1 by 2 power 9 by 2. Right? This is 9, not A. 9 by 2. Because this is a 9-dimensional space. When L2 of 3 into 3, L2 of NM, it will be 3 into 3, 9-dimensional times this 0, 0, 0 plus 1, 1, 1. Okay. Yeah. This will be in C2 tensor. This is in C2. This is in C. This is in C2 tensor. C2 tensor. C2. Okay. And we have something C2 tensor 9. So this you take 3 times. And another thing is 2 power 9 by 2. This 0, 0, 0 minus this 1, 1, 1 takes 3 times. This is a 9 tuple. 9, this is contained in Z2, L2 of Z2 tensor 9. Okay. So this is the code. Our code is this. There are many other code. If you are not confused, I will explain more on this.